magnetic field is created surrounding the wire carrying an electric current. Now, if another wire carrying some current is placed in the neighborhood, then the magnetic field of the first wire acts on the other wire. This is the magnetic force between two wires. This is why the wires carrying currents experience a mutual force. This shows that to understand this force, one must know the force acting on a conductor carrying a current when placed in a magnetic field. If a straight wire of length L carrying a current I is placed in a magnetic field vector B, then the force acting on the wire is given by vector F is equal to I vector L cross vector B. The law giving this force was established by Ampere through his experimental studies. It states, when a current element I vector dl is placed in a magnetic field vector B, the force acting on it is given by vector df is equal to I vector dl cross vector B. This is illustrated as the rule known as the right-hand rule. That is, if the right-hand palm is extended with the fingers pointing in the direction of the magnetic field and the thumb giving the direction of the current, the force on the conductor is in the direction of normal current coming out of the palm. Consider now two very long conducting wires placed parallel to each other with a distance y between them and carrying the currents I1 and I2 in the same direction. Both the wires have been placed parallel to the x-axis. The magnetic field at a distance y from the conductor carrying the current I1 will be vector B is equal to mu 0 into I1 upon 2 pi y into k cat vector. The strength of this field is the same at all the points of the wire carrying the current I2 and is directed along z-axis. Therefore, the force acting on the second wire over its length L will be vector F is equal to I2 into vector L cross vector B is equal to I1 into I2 into mu 0 upon 2 pi y into vector L cross k cat vector. That is equal to I1 into I2 into mu 0 upon 2 pi y into L into I cat vector into k cat cross vector, because current I2 being along the x-axis. Therefore, vector F is equal to minus mu 0 upon 2 pi into I1 I2 L upon y into j cat vector. Equation shows that the force vector F is acting on the wire 2 in the y direction, which is towards the wire 1. So, it is an attractive force. If I1 is equal to I2 is equal to 1a, and y is equal to 1 m, then the force acting on 1 meter length of the conducting wire is modulus of vector F is equal to mu 0 upon 2 pi, that is equal to 4 pi into 10 raised to minus 7 upon 2 pi, that is equal to 2 into 10 raised to minus 7 Newton. This result is used to define the ampere as follows. When the magnetic force acting per meter on two very long, in principle infinitely long conducting wires carrying identical currents and placed parallel to each other at a distance of 1 meter in vacuum is 2 into 10 raised to minus 7 Newton. The current passing through each wire is 1 ampere.